Hello, YouTube channel. If you are coming in just now to my YouTube channel and you are expecting to see Raymond sums, that will be in the next video. Today's video, I don't even want to introduce any symbols or anything because I do not want to scare anyone. We are just going to find area under curves utilizing the most basic shape in geometry, which is, I guess technically it's a square, but a rectangle. We're going to be using rectangles. And by definition, a square is a rectangle, but a rectangle is not a square. Or is it the other way around? No, it's a square is a rectangle, but a rectangle.
All squares are rectangles, but not all rectangles are squares.
Yeah, all squares are rectangles, but not all rectangles are squares. There you go. Yeah, kind of got me. So there it is. So let's chat. If I have a train, so this is an x-axis, a t-axis, and a y-axis. We're going to call this the velocity. And I'm going to say that this train is going in meters per second. Or you know what? No, we're in America, so we're going to say miles per hour. Miles per hour. And the time here is in hours. And let's just say that this train has just been traveling and has been going at a constant, what's a nice number, 50? At a nice 50 miles per hour all the time. So it's constant 50 miles per hour. So this train travels 50 miles per hour. And let's say it travels 50 miles per hour for 3 hours. In 3 hours, how many miles have I traveled?
150.
Yes. Viacana answered correctly. She told me that in 3 hours, I travel 150 miles. Here's what I want you guys to observe. Does this area equal 150?
Yeah.
Yes, I hope that you guys are saying yes to yourselves. Yeah, let me fix the camera a little bit because it's aiming a little low. There we go. It's actually a laptop, but whatever. So yeah, it is really 150 here. That area that I shaded is 150. So I want you to recognize that area under a curve, a special curve. What type of curve is this? It's a velocity time curve. Area under a velocity time curve gives you the distance traveled. Well, I shouldn't use the word distance. I should be using the word displacement. But if the velocity is always positive, then it's the distance traveled. Do you guys agree with that statement? Okay, so here's the next question for you. So you don't need calculus for that. That's simple. So Chavez, why are we learning calculus? Why are we doing what we're doing right now? Well, what if the train did not move at a constant 50 miles per hour? What if my velocity varied within time? What if my velocity varied? The question to you is this.
Those are rectangles.
Yeah, they're not rectangles. The question to you is this. Will the area under the curve of this velocity time graph still be distance traveled?
Yes.
And I hope that you answer yes, it will still be distance traveled. But notice, now you have irregular shapes. No longer can you do, oh yeah, we can, like this one right here, I guess I'll call this A. A was just a nice rectangle. And then I'll call this exhibit B. And exhibit B, it's an irregular shape. I guess it's kind of sinusoidal because I put two humps. That reminds me of that song by Fergie Ferg. Okay, anyways, you see, all these words always remind me of music and whatever. Anyways, as you can see, there's two humps, but it's an irregular shape and you cannot find the distance traveled. Like you can't find it. You can with calculus, but the way you have it right now, you can only probably do like at best an estimate. Does that make sense to you guys? Okay, so now that we know that, we're going to utilize these three, and I guess I should have left room to write them. I'll write them up here. So there's something called LRAM, MRAM, and RRAM. And let me tell you what each one stands for. Relax. LRAM. LRAM stands for left. I think it's leftmost, or it might just say left. Oh, well, left, maybe leftmost. Rectangular. Approximation. Method. It might be better. Write the word left, and then if you want to write leftmost, that's fine. RRAM Take a guess. Take a guess what RRAM stands for.
Right.
Right. Or it might be the word rightmost, but I'm just going to put the word right. Right, rectangular approximation method. And I guess the name is important, but the difference between right and rightmost is not much, right? I guess if you want to go to YouTube and type LRAM calculus, they'll tell you, put YouTube. What does LRAM stand in calculus? And tell me if it says left or leftmost. Take a guess for M.
Middle.
Yeah. Mid rectangular approximation method. And we're going to do all of them. There is one more. There is one more type of approximation. We will do that one sometime next week. The one that we're missing is trapezoidal. And guess what? We're going to use trapezoids. It's in the name, trapezoidal. Oh man, these guys are so funny. I just love life. Life is, everything is so entertaining. Like well, at least for me, I'm easily entertained. I'm like a puppy. Puppies, you just walk by them and they're like, oh, and they wag their tails. But yeah, I think dogs in general are just very easily entertained. But cats, why do not, I mean, I don't know. I get sad because, well, I'll stop talking, guys. You know what? Let's just talk business. Okay, real quick, 5 seconds. Have you ever gone to someone's house and there's a cat that you really want to pet, but every time you go towards the cat, it just runs away?
Yeah.
And it makes me so sad. Like, cat, why don't you love me? But if you go to anyone's house and there's a dog, the dog is so happy. Like, oh, hey, what's up? What's up? Like, it's like you're bros already. What's up, dog? Like, what's going on? Ah! Like, you don't even know the dog and they're excited, but not a cat. A cat, you go up to him like, hey, I want to pet you, kitty. And the cat's like, what are you doing? Get away. And it just runs. And I'm like, man, what the heck? Like, okay, I had to vent, guys. I'm sorry. So that makes me sad. So if I visit someone's house and there's a cat, I want to pet it. And the cat's like, nah, don't pet me. Get away from me. All right, here we go. A particle starts at x equals 5. So I'm reading example 1, guys. So I'm at x equals 5. That's the position. And moves along the x-axis with velocity v of t equals t squared. All right, so I have a particle. And it's just moving on the x-axis. That's all it's doing. So here's the x-axis, and here's a particle. And it starts, so here's x equals 5, and that starts when time is 0. And so imagine that you got something on the x-axis, and it's either moving left or right. In this case, it's moving right forever. For a time t greater than 0. Using 6 subintervals of equal width, approximate the total distance traveled from t equals 0 to t equals 3 using LRAM, MRAM, RRAM. Once you find the distance traveled, where's the particle t equals 3? Okay, so there's a lot going on. So let's just go real slow. First, I'm going to do a sketch of my velocity time graph. This is not a sketch of the particle. This is just a sketch of the velocity and the time. So the velocity and the time is dictated by, boom, t squared. So here's my velocity. It doesn't have it in hours. It doesn't have units. So it just has that and then time. So how does t squared look like? I'm going to exaggerate it, and a t squared looks like that. And I'm going slow. All right, next. What they want me to do is find the distance traveled. So if I want to find the distance traveled, just like I did up here, do you guys agree that I have to find the area under the velocity time curve?
Yes.
Yes. So that's all I'm doing because I want to know the distance traveled. So remember, just in case you're wondering, like, Chavez, I don't understand. Well, go back to your train example. If a train is going 50 miles an hour for 3 hours, how much has it traveled? 150 miles. How do we do that? We found the area under the curve. So we're going to find the area under this curve, and I'm going to really exaggerate it. You know what, guys? I'm going to erase it because I'm going to really exaggerate it. So we're going to use up the whole space. Let's use up the whole space. I'm sorry, guys. I should have told you that. You can always do it on the side, do it on the side on a separate sheet of paper. We're going to use up the whole space. From 0 to 3. So here's 3 seconds. Here's 1. Here's 2. And I'm going to go slow. I'm going to label it. LRAM. And I'll wait until you guys are done. Let me know. Give me a thumbs up whenever, like digitally, give me a digital thumbs up whenever you guys are ready. Yeah, I should start doing that. Forgot about that. I see no digital thumbs up. So does that mean they're not ready yet? Or? Oh, okay, we got 1, 2, 3. Hey, I like that, Alaman and Mazuka. You guys painted your thumbs, and Curtis, you guys painted your thumbs. Everyone's thumbs are like Homer Simpson, but you guys, not you guys. All right, now we're ready. So I'm using LRAM. So what that means, the key word is L. Well, that's not even a word, that's a letter, right? The key letter is L. So we're using the leftmost, we're cutting up into each, man, I can't even talk. I have all these ideas in my head that are going through my head, but I can't even talk. We are using 6 rectangles because they told us n equals 6. And I'm finding I need to fit these rectangles between 0 and 3. Now, each rectangle has to have equal width. So to figure out how the width of each rectangle, all I'm going to do is go 3 divided by 6. So each rectangle has a width of half. That's your delta T, I guess. Does that make sense to everyone? Okay. So again, I'm going to go ahead and put little marks in between. So those are all my rectangles. Chavez, I don't see any rectangles. Don't worry, we're about to put them. And I'm going to go slow. My first rectangle between 0, so here's 0, that's 0.5, that's 1.5, that's 2.5. That's how thick each rectangle is. Each rectangle is a half. So my first rectangle, you're going to go at the leftmost point on the curve. My first rectangle has a height of 0. So it's right on the t-axis, or x-axis if you want to call it that, but I don't want to confuse you. This is time. The second rectangle, go to 0.5 and go to the curve and put a point on the curve. And go down. And then from there, you already connected it. Now you're going to go right like this. And there it is. There's my first rectangle. Well, my first rectangle, that's a legit rectangle. Now you're going to go, and don't worry, I'm going to slow down so I can see you guys still drawing. I'm going to go to 1. I'm going to put a point on the curve. I'm just going to go straight down like that until I hit 1. And now I go back to the point on the curve and I make another rectangle until I get to 1.5, straight down. There's my, technically that's your third rectangle, but it's your second one. It's your second real rectangle, but your third iteration there. And I'm going to continue the process. I go to 1.5, point. There it is. I go to 2. I go to 2.5. And those are my 6 rectangles. Are we okay, guys? All right. I'm going to find the area. How do I find area of a rectangle? Length times width, or width times height in this case. So area of the first, so here we go, area. And don't worry, I'm going to show you all the steps. The first rectangle has a width of half and a height of 0 squared. Because remember, the equation is t squared. Plus the second rectangle, technically, has a width of half and a height of whatever 0.5 squared is. The third rectangle, 1/2, 1, squared. You guys get the picture? Go all the way until 2.5.
I just don't know why we have to square it.
Oh, this, so Viacana said, I don't understand why we're squaring it. The height of rectangle number 2 is whatever the y value is. This curve is y equals, or v equals t squared. Does that make sense?
Yes.
So to figure out the height, you got to square the x value or your t value to see what the height is. To figure out the height here, well, 1 squared, that height is 1 here at that one. To figure out the height at 1.5, you got to square the 1.5.
Figure it out.
All right. Is there an easier way to do this one? Yes. Notice there is a half on every single term. So you can factor out a half and go 0 squared plus 0.5 squared plus 1 squared plus 1.5 squared plus 2 squared plus 2.5 squared. And I don't have a calculator. I have Desmos. I'm trying not to log out. And you know, so yeah, just do that real quick and then I'll tell you what I get. Let's see who's faster. I got 6.875.
More together.
Is that what you guys got? Yeah, whatever you got.
I almost forgot what, I forgot how much I have.
I had a professor, guys, who would do what I'm doing right now, exactly like that. And I would always get something different than he would get all the time. But I would never speak up because I always just assume like, well, I guess I'm wrong because that's what he got. And then we continue and he's like, nope, these numbers don't make sense. I made a mistake. No one corrected me or blah, blah, blah. This was not correct. And inside I'd be like, oh, I knew it. I was right. But I never had the courage to speak up. And the whole time I always thought I was wrong. I mean, not always. It didn't always happen, right? But because sometimes I was wrong. All right, there it is. The question. Here's the question. This is obviously, it doesn't have any units, guys, but this is the distance traveled. The question is this. Using LRAM, is that an over approximation, under approximation, or is that the perfect answer?
Under.
It's an under approximation because there's still all these little gaps that you did not take advantage of. Does that make sense, guys? All right, now we're going to do RRAM. And look, that's why I have the second page all blank. So now I'm going to do RRAM. So again, I'm going to take up half the page. And I'm going to draw the velocity curve again. And again in blue, 0.5, 1.5, 2.5. And I'm doing rightmost. Again, you already know that the width of each rectangle is a half. And you know that because the interval is 0 to 3 and I want 6 rectangles. So, and I'm going to go real slow. My first rectangle between 0 and 0.5, you're going to use the rightmost point on that interval. Put a point on the 0.5, go down. And now in this case, you're going to go all the way left until you hit the y-axis or your v of t axis, whatever that is. There's your first rectangle. Go to the 1, go down, and then go all the way to the left like so. There's your second rectangle. Continue the pattern. Oh, man. This one will have true six rectangles. I'm going to go ahead and find the area. 1/2, half times height, half times height. I'm going to factor out the half already. 0.5 squared, 1 squared, 1.5 squared. If you already have it in your calculator, all you got to do is scroll up. And luckily for me, I already have it in my calculator. Scroll up, delete the 0 squared, which I guess you don't have to, right? Because 0 squared is 0. I got 11.375. That was Spanish, by the way. If I could speak Portuguese, I would, but I can't speak it. So 11.375, guys. And this is a what? Overestimate, underestimate? And now we're going to do MRAM. And what color do you guys want me to use? I don't have pinkness. Actually, yeah, I do have pink. It's very light. Okay. Yeah, I'll do it down there. I'm exaggerating the graph like I have all the others. The one looks a little out of place there. There we go. I think we're in good shape. So how are we going to do the middle one? Like this. The middle between 0 and 0.5 is 0.25. So go to the middle, 0.25, a little bit above the curve, a little bit below the curve. So you should have a rectangle that's half above, half below. Don't worry, I'm going to continue. The rectangle between 0.5 and 1, so go to 0.75, a little bit above, a little bit below. Go to the 1.25, the middle, a little bit above, a little bit below. You can see it for the rectangles that are bigger here. 1.75. And those are my 6 rectangles right there, guys. How do I calculate this area? It's still half. You can still have your half factored out. But in this case, instead of squaring the 5 or the 1, you're going to be squaring in the middle. So you're going to square the 0.25. You're going to square, and then you can just go, you can just add 0.5 to that or add 50 cents, however you see it. 0.75 squared plus 1.25, 1.75. All those numbers you got to square, guys. So don't just add them up, square them. 2.25, and finally 2.75. So that you're just going to have to do a new line, and I have my calculator here. It's going to take me a little bit. Here's my calculator. So follow along with me. See if you guys get the same thing that I got. 0.25 squared. Okay, I got now we cannot call that perfect. It might be perfect. It might be perfect. A little bit above, a little bit below. Don't worry, we're going to give you the answer in a little bit, guys. And we still haven't even answered the question. Not all of it. We've just answered the distance part. Okay. Okay, is everyone ready for the next step? Don't worry. Okay, we're good. All right, so notice, what do I have here? This table below, for example, 1, the total distance traveled with n sub-intervals. So look, we did this one right here. Let's see, did we get those same numbers? Did we get 6.875 for LRAM? Did we get 11.375 for RRAM? Yeah, we did, right? Okay. And did we get 8.9375 for MRAM? Excuse me. That was supposed to be a yeah, not a hiccup. Yeah. So there it is. It worked. So look what's happening. So here's where calculus is coming in. If you were to do this by hand for 12, it would take you a while. Look how long it took us just to do 6 rectangles. Look at this, 24, 48, 100, 1,000. Do you think the AP exam is going to tell you to do this with 1,000 rectangles by hand? No, they're not. The most rectangles I've seen on the AP exam by hand, I think is 12 with no calculator. Wait, with a calculator, 12. Without a calculator, I think they'll do 6. So they're not going to ask you a lot.
How are we supposed to square it? No.
Oh, it'll be something that you can do. You know what I mean? If you have a calculator, then you'll have the calculator to square. All right, take a guess. Oh, not take a guess. What is the distance traveled by this particle? By looking at this table. And no yawning, that's a demerit. I'm kidding us. 9. How'd you get that, Viacana?
It's like going between 9 and 9.
Okay. Check it out. Viacana said because it looks like this, they're all approaching 9. That is so true. Put that on the side. Put in there somewhere as n approaches infinity, all methods, all LRAM, MRAM, RRAM, all approach 9. All of them. So you can already see where calculus is coming in, guys. The n approaches infinity. Look at this. Look at LRAM. 6.87, 7.9, 8.44, 8.72, 8.86, 8.89, 8.98. It's approaching 9 from the left. From the middle, look, all of those numbers are converging to 9. From the right, 11.3, 10.1, 9.57, 9.28, 9.13, 9.01. All of them are getting closer and closer to 9. Isn't that cool? You guys are like not impressed here. All right. I thought that was cool, guys. Oh no, I put the same problem on the activity today. But I did put LRAM and RRAM. Okay, no big deal. Sorry guys, I just realized I was changing the graph today and I just realized that I put the same equation on the graph that for the activity. It says example 2. If f is positive, continuous, increasing function on AB, then LRAM gives an area estimate that is less than the true area under the curve. So let's see if that's true. So we just did, it wants Positive, continuous, increasing. Oh, well, we have that over here. LRAM. Does LRAM give, is that a true statement or is that a false statement? I already forgot what the statement says. LRAM gives an area estimate that is less than the true area. Yeah, that's a true statement, guys. True statement. See curve, see LRAM curve in example 1. Does it also work for the other continuous? Yeah, always. Yep, it works. All right, example 3. If an MRAM sum with n equals 4 rectangles of equal width is used to approximate the area enclosed the x-axis in the graph 4x minus x squared, the approximation is? Okay, first of all, guys, do you know how this graph looks without a calculator? Factor out an x, and you get 4 minus x. So you have zeros at 0, and you have another 0. This is y equals, right? At 4. So remember from algebra 2, if these are zeros, that means your vertex happens at 2, and it has to look something like this. Now that you know that, and I think you can use a calculator on this one, by the way, it wants us to use 4 rectangles. So we're just using these rectangles. They're all the width are the same, and they want us to use the middle one. So mid, rectangle 1, rectangle 2, and rectangle 3 is actually going to look the same as rectangle 2. And then rectangle 4 looks like that. So there's my visual for my visual learners. How do I get the area? Well, remember, it's just width times height, width times height, width times height. If you get confused, do it the long way. The width of the I'm going to label my rectangles, guys. So I want to make sure that you guys are taking good notes. So I'm going to label these. And then once you guys are really beast, you no longer have to label. So area of rectangle 1, so here it is for good notes. It's going to be 1, width times height. All I'm doing is width times height. 1 times the height. What is the height? 4 times 1 minus, oh, no. We did the middle. The middle is 0.5. 4 times 0.5 minus 0.5 squared, whatever that is. I don't know what that is. I'm going to find out. Rectangle 2. And rectangle 2 and 3 should have the same area, by the way. 1 times 4, and we're using the middle, 1.5 minus 1.5 squared close. Rectangle 3, 1 times 4 times 2.5 minus 2.5 close squared close. By the way, rectangle 2 and rectangle 3 should have the same area. So we'll figure it out right now. 1 times 4 times 3.5 minus 3.5 squared close. All right, so Viacana, you want to take care of 1 and 2, and I'll take care of 3 and 4? And then you guys check to see that we got them right. Okay, what'd you get for 1? Oh, wow. Oh, yeah, it's a metric. I didn't even think about that. I thought about 2 and 3, but I didn't think about 1. 1 and 4 should be the same. And then 2. What'd you get for 2? Perfect. Yes, rectangle 1 and rectangle 4 should be the same because it's symmetric. I don't know why I didn't even think about that. I did think about it. I said 2 and 3, but I didn't even mention 1 and 4. All right, let's add them all up. 1.75 times 2 plus 3.75 times 2, and I get 11. And there it is. All right, we got another one. I feel like DJ Khaled. You guys might not know. You guys are too young. Do you guys know who DJ Khaled is? Oh, I mean, I don't know. That guy's been around for like 2 decades already. So I'm being serious. If you think I'm joking, it's really hard for a musician to be popular for more than one generation. It really is. So the way Drake and DJ Khaled have been able to stay around for going on almost 2 decades, I think that's amazing. All right, let's see. An LRAM sum with 4 equal subdivisions is used to approximate the area under the sine curve from 0 to pi. So you got to know a little bit of pre-cal, not even extreme, guys. What is the approximation? I don't know what the approximation is. Let's find it. So I'm gonna draw my sketch. Hopefully you remember that sine of 0 is 0 and sine of pi is 0. So here's my sine. I'm gonna exaggerate it. My sine curve, exaggerate it. It's supposed to be symmetric. The highest point should be at pi over 2. And because I want, how many rectangles do I want? 4 equal subdivisions. So pi divided by 4, each rectangle is pi over 4. That's a width. So let's see if I can cut it perfectly. Half of pi over, that's pi over 4 right here. And this guy has to be 3 pi over 4. Okay, I got it, guys. So make sure you know what you're doing. Don't just write randomly, little whatever. So all we're doing is putting rectangles in here, guys. That's all we're doing. Let's see. What are we doing? Leftmost, rightmost, or middle? Leftmost, L. We're doing leftmost. L for loser. Okay, well, I'm sorry, YouTube. Oh, you can't. Oh, YouTube can't see this. No, I'm not sorry, YouTube. All right, here we go. Each rectangle is pi over 4 width. So here's my first rectangle. It's like I don't have any. It's like you don't have a rectangle because you're literally on the line. You got to use the leftmost point. The second rectangle between pi over 4 and pi over 2, use the leftmost point. There's my second rectangle. My third rectangle, you got to use the leftmost point between pi over 2 and 3 pi over 4. So we're using the pi over 2, which happens to be the highest point on the curve. So this one's going to be all above. And then my fourth rectangle, use the 3 pi over 4, go all the way to pi. And there it is. We just use the left, we just use LRAM. All right, let's see if we can find the area, guys. So pi over 4, let's see, the height of the first one, I guess we'll say sine of 0 plus sine of pi over 4 plus, and I'm going to erase this part right here. Hopefully you guys already took your good notes there, or write it somewhere in the top, plus sine of pi over 2 plus sine of 3 pi over 4. I hope no one's confused. I'm going to explain what I'm doing. I'm doing width times height, but I factored out the width. Sorry, guys. If you guys see me looking over there, it's because Viacana's over here. So every time I do this, I'm looking at her. So does everyone know that I factored out the width already? So I'm just doing the height. Width times height, width times height, width times height, width times height. Pi over 4. Sine of 0. Well, sine of 0 is 0 plus sine of pi over 4. Pi over 4 is square root of 2 over 2 plus sine of pi over 2. That's 1. So you got to know a little bit of pre-count, not a lot, but a little bit. And then finally, sine of 3 pi over 4. Square root of 2 over 2. Let's see. Were they nice and did they put it in this format? Yeah, they were nice to us. It looks like it's letter C. Are we still doing okay, guys? Okay. Oh, what? Oh, okay. I was like, man, this looks like a lot. Okay, it is a lot, but don't worry, we're done. We're not going to write anything. I just wanted to put something in here for the future medical people, because I think like the engineers, like Ms. Mazuka, the engineer, she can see how all this is going to be relevant. Like, because we're obviously dealing with particle motion here, right? But what about for you medical people? So I just want you guys to see. Look at this. Let's read it together. The number of liters of blood your heart pumps in a fixed time interval is called your cardiac output. Oh, okay, that's cool. So that's what that is. I know you guys already knew that. For a person at rest, the rate might be 5 or 6 liters per minute. Oh, that's cool to know. I didn't know that. I really didn't. I didn't know that. During strenuous exercise, the rate might be as high as 30 liters per minute. Wow, that's a lot. It might also be altered significantly by disease. How can a physician measure a patient's cardiac output without interrupting the flow of blood? One technique is to inject the dye into a main vein near the heart. The dye is drawn into the right side. The dye is drawn into the right side of the heart and pumped through the lungs and out the left side of the heart into the aorta, where its concentration can be measured every few seconds as the blood flows past. Wow, that's cool. The data in the table and plot shows the response of a healthy resting patient to an injection of 5.6 milligrams of dye. Wow, that is real cool. So look what they're doing, guys. They're injecting someone with a dye, and then the aorta, I don't know where the aorta is, somewhere like up down here or whatever. And then they're measuring the concentration of that dye, and then they're just finding area under the curve to see how much blood has been flowing through this person. Isn't that cool? See, look at the calculus at play. So it says the dye concentration in the table plotted, blah, blah, blah. Time is measured from 0. The dye concentration is 0 at the beginning, while the dye passes through the lungs and then rises to a maximum at about t equals 9 seconds and tapers to 0 by t equals 31 seconds. Wow, that's fast. The graph shows dye concentration measured in milligrams of dye per liter of blood as a function of time in seconds. How can we use this graph to obtain the cardiac output measured in liters of blood per second? The trick is to divide the number of milligrams of dye by the area under the dye concentration curve. You can see why this works if you consider what happens to the units. Wow. So now you are ready to compute like a cardiologist. Well, I don't know about that, but thank you, Demano Waits. Isn't that, I thought that was really cool stuff, guys. So I hope that now that you're doing calculus for you future medical people, I hope that you can see how calculus is going to help you in your work. Now, are you going to be doing calculus when you're a doctor? No, you're not going to be literally calculating it. The machine is doing this. But you can understand, like, someone had to program the machine. So someone had to know about calculus, about the ideas of calculus to figure all these things out. So you as a doctor already understand, like, oh, yeah, this machine is just measuring the dye concentration, and I'm measuring the area under this curve, and that's from your calculus days. So you know the basic concepts. So you can see why doctors are so smart. They took calculus, not just because of that, right? They did all the years of medical school. But you can see how math is helping doctors. Okay, I'm getting too excited here, guys. I'm gonna stop. But I hope that you can see the joy of how math is everywhere, not only for engineers, also for doctors, also for scientists. Also it's everywhere. It's all over the place, guys. All right, I'm gonna stop sharing, and I'm gonna go back because you